Right now, as you're sitting there, there's a hidden electrical symphony playing inside your body. It's incredible, right? Every single thought, every heartbeat, every tiny movement, it's all powered by a microscopic storm of biological electricity. So let's dive in and see if we can read the sheet music. For, well, pretty much all of human history, this entire world was completely invisible to us. But now, biomedical engineering has given us these amazing tools to not just listen in on the symphony, but to actually understand its language. So in this explainer, we're going on an incredible journey. We're going to follow one of these signals from a tiny spark inside a cell all the way to a life-saving diagnosis. So think of this like a road trip. We're going to follow a very specific path, step by step, to see how this faint, almost silent whisper from our own biology gets translated into information so powerful it can literally save a life. And here it is. This is our map for the whole journey, the biomedical instrumentation pathway. It's got 4 key stops. It all starts with the biological system. That's the source of the signal. Then a transducer has to catch it. After that, a signal processor cleans it all up. And finally, we get a useful output, which might even lead to a direct intervention. So let's start at the very beginning, step 1. Okay, so first things first, where does this electricity even come from? I mean, we're not plugging ourselves into a wall, right? To find out, we have to go microscopic, to the very origin of what we call biopotentials. Our whole story starts inside just one of the 100 trillion cells that make you, well, you. Each cell is kind of like a tiny saltwater battery, and it's floating in this sea of electrolytes, things like sodium, potassium, and chloride. The real magic happens right there at the cell membrane, where the cell keeps an uneven balance of these charged ions, inside versus outside. And that imbalance, that creates an electrical potential. And check this out. This slide shows the whole game. On the left, you've got the cell in its resting state. It's polarized, just sitting there holding a negative charge of about minus 70 millivolts. It's literally a charged battery, just waiting. But then, when it gets a signal, bam! Sodium ions rush in, and for just a millisecond, the charge flips from negative to positive. That huge spike you see on the right, that's the action potential. That is the signal. That's the fundamental bit of information we're chasing. Okay, so we have our signal, this tiny, fleeting electrical spark. But how in the world do you actually grab onto that? How do we build a bridge from our wet, messy biology toward dry, precise technology? Well, following our map, we're now at step 2 of the pathway. We need some kind of device that can listen to that biological, ion-based signal and convert it into an electrical signal our machines can actually read. We need what's called a transducer. And in our world, that transducer is the electrode. This is it. This is the critical point of contact, the real human-machine interface. Its one and only job is to listen to the conversation happening with ions in the body and translate it into the language of electrons flowing in a wire. It's a bioelectric interpreter. But, and this is a big but, this is where we hit our first major hurdle. The body is an electrically noisy place. You've got muscle twitches, other nerve signals going off, even just the electrode moving on the skin can create interference. All this noise has a clinical name, an artifact. And the danger is that this artifact can completely drown out the tiny, meaningful signal we're desperately trying to hear. So how do engineers get around this? Well, with specialization. It's a right tool for the right job kind of thing. There isn't just one type of electrode. There's a whole toolkit. If you want to listen to a single cell, you need a delicate microelectrode. For the big picture of the brain or the heart, you use non-invasive surface electrodes. And to get way down deep into a muscle, you use needle electrodes. Each one is custom built to get the cleanest possible signal from its specific biological target. So we've captured the signal, but honestly, it's still really faint and messy. It's like trying to hear a whisper from across a crowded, noisy room. Before it can tell us anything useful, we have to clean it up, and we have to seriously turn up the volume. Which brings us right to the heart of the whole machine. Step 3, the signal processor. This is where the raw, messy data gets a major league upgrade. And wow, this slide is the perfect before and after. On the left, that's what the electrode actually picks up, a weak, fuzzy, noisy waveform. But after it goes through the processor, look what comes out on the right, a powerful, clean, and just beautiful signal. So what on earth is happening inside that black box? The hero of this stage is something called a bioamplifier, and it has 2 absolutely critical jobs. First, the power boost. it has to crank up the voltage of that tiny signal by a factor of over 100,000. That's like turning the sound of a pin dropping into the roar of a jet engine. And second, noise rejection. It uses some really clever circuitry to spot all that background noise and just subtract it, leaving only the pure biological signal we care about. All right, we've done it. We've found the signal, we've captured it, we've cleaned it up, and amplified it. Now for the payoff. This is the moment where that pure data gets turned into knowledge, into a diagnosis, and maybe even into action. We've reached our final destination on the map. Step 4, the output and intervention stage. So after all that work, what can this clean signal actually do for us? Well, it turns out each signal tells a completely different story. A signal from the heart gives us an electrocardiogram, or ECG, which is crucial for cardiac analysis. A signal from the brain? That gives us an EEG for checking out neurological activity. And from the muscles, we get an EMG to check how our nerves are firing. Each one is like opening a brand new window into our health. Let's just take the ECG, for example. I'm sure you've seen this waveform before. It's not just a random squiggle, it's a super precise map of electricity flowing through the heart. That little P wave shows the atria contracting. Then that big QRS spike, that's the powerful ventricles firing. And the T wave shows them resetting for the next beat. A doctor can read this thing like a book. It's amazing. And it's not just the heart. With an EEG, we can create these incredible colorful maps of electrical fields across the entire scalp to see what the brain is up to. With an EMG, we can measure the exact speed and strength of nerve signals traveling through your arm or leg to diagnose damage. It's this incredibly versatile technology that turns these invisible sparks into detailed blueprints of how our body is working. This is all fantastic for monitoring and for diagnosis. I mean, it's life-changing. But what happens if the system detects a critical failure? What if just knowing about the problem isn't enough? Well, this is where our pathway takes one final mind-blowing step. The system can actually close the loop. When the instruments detect, say, end-stage heart failure, they can do more than just sound an alarm. They can trigger an intervention. They can activate something like a ventricular assist device, or VAD, which is a mechanical pump that literally takes over the job of the failing heart. And the best part? It uses the body's own electrical signals to regulate its speed. The machine doesn't just read the body anymore. It becomes a part of it. And that completes our entire journey. Think about that. We went from a tiny flicker of ions inside a single cell all the way to a sophisticated machine that can literally keep a person alive. We've learned how to read the body's hidden electrical code, and by doing that, we're now learning how to help rewrite its future. Which just makes you wonder, what code will we learn to read next?